Hey, come in.
Yeah, just, that's fine.
Come in, sit down now.
Perfect.
No mouse? Do you have any counts?
I don't need a mouse.
Nope.
No, I'm fine with this. Oh, wow. People are coming in.
And we'll just wait till you sit down, and then I'll give you a big clap. Cool. Thank you.
Okay, good.
Okay, thank you so much.
Yeah. Thank you. Hi, everybody. My name is Jens Mönig. I'm a researcher with SAP. And this is my friend and colleague, Bernard Romagoza, a researcher with Arduino. And we'll be presenting a graphical programming language that we're working on together with our friend Brian Harvey, who's a professor at UC Berkeley. And the language is called Snap, which is kind of a generic name. And it's got the name Build Your Own Blocks. So what is Snap about? Snap is, anybody know Scratch? The language Scratch? Who knows Scratch? Awesome. You all just know Scratch. Anybody know Snap? Okay, great. So I'm going to show you something new. Okay, Snap has been created for a new course at UC Berkeley that's in place now for 6 years. They replaced the old CS10 course, which is the introductory computer science course for non-CS majors, with a new course that's called The Beauty and Joy of Computing. And just changing the name and switching over to a language that is more accessible has kind of, attracted more underrepresented minorities to the course. So for the first time in UC Berkeley history, actually, the course has a higher number of females than males in that course. And that's partly because formerly it was named Introduction to Symbolic Programming. And so names matter, and accessibility is something that is not just, for disability issues, but also for regular people. So the development of Snap has been for a long time kind of my side project as I was a programmer and lawyer for another company. But then we got kind of lucky. We got some funding from the National Science Foundation. We got my employers to kind of fund it and let me work on it. It's been Neosoft and now SAP and Y Combinator also. There's a curriculum, the Beauty and Joy of Computing curriculum, that's been developed at UC Berkeley and now at nationwide at Education Development Center. And it's also an APCS Principles course. That's a kind of new kind of course in the United States that's sort of like a centralized, standardized course for the big ideas in computer science, and BJC, the acronym for Beauty and Joy of Computing, is part of that, is one of these courses. And since October now, since the last semester, we're kind of dissipating it nationwide. There's a MOOC on edX, and there's a project to bring this course to 100 high schools in New York City, and we've been working with them for the last year. And they're kind of using this course and also using this language. So the language, which is why we're here, it's web browser based, it's pure HTML, JavaScript, so it runs in the browser. It doesn't have to be installed, which is a problem with schools. If you try to install software, sometimes they won't let you. It's been translated right now into 39 languages, most European languages, but also some Asian ones. It's, of course, free in Libre and open source, so it's all on GitHub. You can fork it, and people have forked it a lot. There's also a free cloud service, so kids can, in school, start a project and then continue working at home by, just logging into the cloud or keep working on it on their iPads. And it's used as a teaching and research platform in many institutions. So, our colleague Brian Harvey coined this term that Snap, which is our language, is basically scheme, but it looks like Scratch. So what does that mean? So from Scratch, we're taking these blocks that stick together, that prevent syntax errors, that look inviting. We've got the 2D cartoonish micro world where there's sprites that can move around against a backdrop, which is called the stage. We've got, the parallelism from Scratch, where things can go at the same time. You don't have to think at the level of ticks in order to make things move, but you have actual, threads and processes. And it's one of the most important things. It's interactive. It's constantly live. There is no compiling run cycle, but wherever you click on a block, it immediately happens. And I'm going to show some of that liveness, which is important to make something self-discoverable. So you don't have to Google how does it work. You can just try it, in a safe environment. So this makes for a low floor, as we say. It's an easy access. It gets you started. But it's also Scheme disguised as Scratch. So from Scheme, we're taking the ability to, not just use the blocks that we give you, but also it's an extensible language. You can build your own blocks. You can build any blocks. And by any, I mean you can even build kind of control structures. It's dynamically typed. So we've got heterogeneous data structures, and we've got lexically scoped variables, which kind of allows us to kind of do real computer science. We have some first-class stuff, including first-class lists of lists that allow us to build model any data structures, and we've got a way to think about blocks using blocks, which is essentially Lambda. So we've got Lambda and Lambda capturing non-local state of variables, and that also allows us to not just model any data structure, but to model any control structure, basically kind of build your own programming language in blocks. And we've got some fun stuff like first-class continuations, just because we're talking about Scheme, which kind of allows for us to build our own, like break things and non-local exit control structures. And because we're encouraging students to use this language to build their own control structures, we have proper tail recursion, so they can model it recursively, because that's a powerful idea to think about and to learn. So this is basically the old battle cry of the Logo community, right? So we got the low floor, but we have no ceiling. We do have a ceiling. Technically you can't do everything with Snap, but conceptually, anything and everything that you can express in a programming language, we want to be able to express in this kind of, kids-looking like language. So there are some other things that we, took from other environments that inspired us, like Smalltalk, Logo, and Self. So we've got more first-class stuff. We've got more ways to work with data. We've got web APIs, so kids can play with robots and drones and stuff. It's extensible with JavaScript, so you got a way to kind of write your own blocks, and even if, it doesn't exist yet, if you need primitives, we can transpile and compile the blocks to other languages, so we can embed it on, little robots, because some of these, like Arduinos, they really enjoy having their sketches kind of natively, because they're low-powered machines. And we can deploy these things as native apps also. And this is basically what we call wider walls. So these are the 3 dimensions that we're talking about: low floor, low entry, no ceiling, so you can stick to Snap and do your PhD in Snap, but there's also a wide variety of things, and there's usually more than one way to do one thing. So we're very encouraging people not to think this is the right way you can do it, but there are different ways, and they should all work. So, let me show you. Okay, good. What's happening? I didn't get my mic. So this is, anybody seen this? This is kind of a project that started it all. It's called V, and what this is it's a little project, and here's an example of a custom block. And this is how we define the block V. So on the stage, what we have is what every Scratch kit will identify as a list watcher. It's a list. Only in the list, there are blocks. And this is something provocative. This is something Scratch doesn't give you. So here we have this function V, and I've kind of slowed it down to see what happens. So I'm just going to let this run. So just kind of slowly you can see what it does. It'll kind of, turn left, move a little, and then run any of these blocks in the list, go back, turn right, run another any of these blocks. Let me just make it a little faster by turning off visible stepping, so I can run this a couple of times and I get some random ends. And now the question that we ask kids, and this is actually how we what happens now? So now I just press the button and there are 2 V blocks in that list. So what will happen if I now run this procedure? Any idea? Any guesses?
W.
W. Any other ideas? Let's just try it. I'm just going to click this. Oh, look, there's kind of some random shapes. Sometimes it'll just do that. Sometimes it'll kind of really go crazy. So we're getting, a fractal because V can now kind of, call itself. And the reason why it doesn't go on forever, like it could go on forever, but, the reason is it's just some statistical probability. It's not going to actually go on forever. And the beautiful thing about, this is we're showing 2 big ideas. And this is what the beauty and joy of computing is all about. We're showing 2 big ideas in this thing. It's a list of procedures. That's procedurous data. Procedurous data is traditionally considered something to be very difficult to understand for beginners especially. But here it's kind of a visualization that's easy for even Scratch kids to get. Procedurous data. And the other way is we're introducing recursion, right? Something that will call itself, and the beautiful example of this is it doesn't even have to have a base case because the base case is just math. So this is kind of the archetypical example. Let me just show you a few things. So what we have in Snap is, for example, 3 plus 4, and if I click on this, I'm immediately getting an example, so I can try this. But I can also prevent this from being evaluated by putting it inside a ring. So now it's kind of protected against being evaluated. And then I can go and I can call it again. And now if I call it, I'm again getting 7. So why is this interesting? And I can kind of call it with a parameter, and I'm getting 8. So this is, I can package something and I can unpack it again, and that's seemingly trivial, but what this actually allows us to do is higher order functions. We can pass on the block and evaluate it later. So we can build our own higher order functions. So here's a map, and this is how map is defined. And we can take map and, for example, have a list. Just the old 1, 2, 3, 4 list, and map the times 2 function over this, and we get a list where each item has been transformed. Or we can have, since this is functional, we can have any function in there. Now this is going to be the square function. We can put in a function that makes a list, and we get a list of lists whose first item is the square of the input number, or we can kind of go even crazier and make a list of lists, which kind of turns out to be a table. So with these kind of simple, seemingly simple features, we can do pretty powerful things in computing. And so this is really what the beauty and joy of computing kind of is all about. So let me show you just one more example of this very quickly. So this is supposed to be the building in which we are. The weather isn't so great, so I took this off the web. My own one didn't have enough colors. So here's an example of first-class stuff. So we've got kind of this first-class costume, and I can look at the pixels in that costume. And so I'm getting a table, it's kind of almost 56,000 rows of, 4 columns, and obviously these are the RGBA columns. And so it's just a list. It's just a list of lists. So if it's just a list of lists, I can take my map thing and do something with it. So I'm just going to, put the first item of the list in the second slot, put the second in the third slot, put the third in the first slot and leave the last one, which is the A, where it is. So this is a function. I'm going to put this function into map and see what happens. And it's going to take a little while. Oh, but here it is. And I can compare these two tables. And if I look at the first number, see this is 84, 120, 204. Now it's kind of rearranged, right? It's just data. So what happens if I kind of redisplay this data? What's going to happen to the blue sky? Oh, look, I can make my own graphic effects. It's just higher order functions. This is just map. This is, to us, what the beauty and joy of computing is all about. I'm going to leave it here to hand over to my colleague, Bernardo Ramagosa, who's going to show you kind of some more concrete things to do with Arduinos and with 3D plotting.
Okay. So basically, it's dangerous to do a live demo. It's even more dangerous when you have hardware involved. And I swear to God this was working last week. I presented it last week. So I'll try it again. It didn't work 10 minutes ago. It might not work now. Let's try it. The idea here is I have exactly the same Snap environment, only that it's a modified version of Snap that lets you interact with Arduino boards, okay? So the first thing you do is you connect to the Arduino board, which I have here. It tells me it's been connected. And now I have a sensor here, and I have an LED here. I'll try to be really fast. So I can try to get the analog reading of the pin where the sensor is connected. If I press on it, I'll get a value. So it works exactly like Snap, no difference. So let me try to plot this. To plot something, we need to have a sprite moving one step all the time, right? And basically, when the X position goes over the edge of the stage, I want it to set to the other edge, right? Okay. What do I have to do with the Y position? I have to map it to the value of the sensor, right? So I'll just set Y to the value of the sensor. And what if I put the pen down now? And of course I'll need to clear the stage when the sprite gets out of stage, right? Yeah. Okay, so if this was working now, you'd see my heartbeat, which you kind of do, kind of. And I can also map this to, again, the real world. And in the real world, I have this LED that would be mimicking my heartbeat, if it was working. I'll try, because these are very sensitive sensors, and they sometimes need to be under a bit of pressure and in darkness. So I'll try to apply some pressure. Yeah. Kind of. Do you believe me? I swear it's my heartbeat. So what we can do is I'll show you a 1-minute video. Oh, what's going on?
Heart rate monitor from.
So this is a heart rate monitor. This is the LED. By the way, this heart has been coded in a language that's another modification of Snap called Peter blocks. So the whole thing is made with blocks. Here I'm trying to get my heart bumping. I'm not very much in shape, so it just took around 10 seconds. And you can see that the graph did actually work. I didn't fake it, I swear. I think I kind of broke the sensor by pulling the cables, I don't know. And so to finish the presentation, I want to show you what this heart looks like in BeetleBlocks. This is BeetleBlocks, and basically it's the same thing as Snap, but now you have a 3D world here, and you have a beetle that receives your instructions, okay? So I can, for instance, have it repeat something 24 times and create a sphere behind it, okay? Cool thing about this is once I have my shape, I can download it as an STL and print it in a 3D printer, or as an OBJ and use it in my game, okay? And since this is Snap, you can have your own procedures, you can have your own more complicated blocks. Like for example, this block that I built that generates a heart shape. I of course copied this from Wikipedia. I looked for a function that draws a shape. I don't know the first thing about mathematics. And let me show you how it works. Now it was in turbo mode, but and so basically the idea here is that blocks programming is serious programming, and you can do pretty much everything. And I don't know if we have time for questions. I think. Yeah? Okay. So I think I'm done.
Questions?
Yeah. Have you considered? I actually used to teach kids with Scratch, and it worked really well. But like after a while, they just kind of grew out of it. Like they hit some wall. I could tell Snap is more powerful, but have you considered at some point offering a way to transition to text-based programming, like within the same tool? Yeah, I mean, you even mentioned it was kind of like Scheme. You could kind of transition to something like that.
Okay, there's a question, like what's the strategy to transition to progress from block-based coding to text-based coding? And I've kind of given talks on this the other way around, like how do you progress from text-based code to blocks-based code? So you got to watch out for the motivation behind this. So once you realize that, working with blocks in a live environment, you're actually working at the AST level of a programming language. You're actually modifying a script as it is running. This is something no text-based language will let you do. It will. There are live coding languages, but they will only, refresh after the next loop, or they'll reset it and restart, And in music, they'll do it, at the next beat or at the next bar. So conceptually, I think we all know that text-based programming works. I mean, that's everybody. I mean, this is coded in text-based JavaScript, underneath. But conceptually, there is no necessity. Conceptually, there are interesting things if you take blocks to the extreme, as we are. And there are really two things about text-based programming that, well, three. First is because my dad is using it, right? So I keep telling kids, but your dad's boss, she's using Snap. Well, maybe at some point, hopefully. And the other way is there are issues, of course. We're looking at blocks in the palette, so this works great for 120 blocks. What if you've got 1,024 blocks, and how are you even going to find them? So I could show you some more, but we've built something into Snap that lets you type blocks. So there's a typing mode, and you could just start typing, and then you get all the blocks, and with just a few keystrokes, you kind of assemble a script. And I've been very inspired to do this, and basically to the point of almost copying it from Greenfoot, from Michael Culling and Neil Brown. Their new frame-based editing, as they're calling it. The Stride editor has been a great source of inspiration to type more complex things. So you don't have to use the mouse to drag it up. You know, start with the control palette, then go an F, then go to the operators palette, drag out, you know, and keep switching. So if you already know there's something like that, you can type it faster. That's kind of one of the main things for power use.